Hello everyone. In this lecture we are going to discuss about the numerical and torque ratio and some simple problems we are going to solve from the gate question papers. Okay. So the first one is a three-phase induction motor has a starting torque of 100% and a maximum torque of 200% of the full load torque. Determine first one slip at which the maximum torque occurs and second one full load slip. Okay, first we'll write the given data. So both the starting torque and the maximum torque are given as a percentage of full load torques, right? So first one, we'll write the starting torque as 100% of the full load torque. Okay. So the second given data is the maximum torque is given as 200% of the full load torque. Okay. So first we have to find out the slip corresponding to maximum torque, S suffix m, and the slip corresponding to full load. Okay. So now from this given two equations, we can write starting torque divided by maximum torque. Okay. So this is equal to, we all know the formula for starting torque divided by maximum torque, that is ratio. We have already derived this one. So the formula is 2 into Sm divided by 1 plus Sm square. Okay. So this is given here. So this is 100% as that of the full load divided by this maximum torque is given as 200% of the full load torque. Okay. So this is 100 by 101. This is 200 by 100. That is 2. So 1 by 2. So this full load torque will get cancelled. So this will be 1 by 2. Okay. So now we can write 2 Sm divided by 1 plus Sm square is equal to 1 by 2 is nothing but 0.5. So on cross multiplication, we'll get 2 Sm is equal to 0.5 into 1 plus Sm square. Okay. So 2 Sm is equal to 0.5 multiplying inside 0.5 plus 0.5 Sm square. Okay. So on rearranging this equation, we'll get 0.5 Sm square minus 2 Sm plus 0.5 equal to 0. So this is quadratic equation in Sm. On solving this equation, we will get the slip corresponding to maximum torque, that will be equal to 0.2679. Okay, this is the required slip corresponding to maximum torque. So next what we have to find out is slip corresponding to full load condition. Okay. So now we all know the torque ratio between full load torque and maximum torque. So already we have derived this one, is given by 2 into Sf into Sm divided by Sm square plus Sf square. So this is a formula we have already derived, the ratio between full load torque and maximum torque. So now this maximum torque is nothing but 200%. 200% of this full load torque. So that is 200 by 100 into full load. Okay, this is kept as such full load. And this is Tm can be written as 200% of full load. Okay, so this will become 2 into full load, and this full load torque and full load torque will get cancelled. The remaining term will be 1 by 2. Similar to the previous case, we will get 1 by 2 or 0.5 over here. So now we can substitute the value for Sm, which we have already found out as 0.2679. Okay. So 2 into Sf we have to find out. Sm value is 0.2679 divided by 0.2679 whole square plus Sf square is equal to 1 by 2 is nothing but 0.5. Okay. So again, we have to cross multiply these two. So in this side, 2 into 0.2679 can be written as 0.5358 SF. This is equal to 0.5 into 0.2679 whole square plus 0.5 SF square. So on rearranging this equation, we'll get 0.5 SF square minus 0.5358 SF plus 0.03588. So again, we'll be getting a quadratic equation in SF. Okay. So on simplification, we'll get the slip corresponding to full load condition as 0.0717. Okay, this is the required slip corresponding to full load condition. Okay. So next we'll solve some simple gate problems related to the torque ratios. Okay. So the problem is the frequency of the stator and the rotor currents flowing in a three-phase 8-pole induction motor are 40 Hz and 1 Hz respectively. The motor speed in RPM is dash. Okay. So first we'll write the given data. The frequency of stator and rotor currents are given. Okay. So the frequency of stator is written as F. So this is nothing but the supply frequency. Okay, 40 Hz in this case. And frequency of the rotor current is given by FR, 1 Hz. Okay. So and then number of poles of the induction motor is given, 8 poles induction motor. So now what we have to find out is, we have to find out the speed of the motor in RPM. So speed is given by 1 minus S into NS. So we have to find out both slip and the synchronous speed NS. So first we'll find out the synchronous speed NS. NS is equal to 120 F by P. So 120 into F is nothing but the frequency of the supply voltage. Okay, here F is nothing but frequency of the supply voltage or stator current. So 120 into 40 divided by 8. So on simplification, we'll get 600 RPM. So this is a synchronous speed. So next we have to find out the slip value. So we already know that the rotor frequency. So frequency of the rotor current, FR is S times the supply frequency. So from this expression, we can write S is equal to FR divided by F. So this is nothing but 1 by 40, or this is equal to 0.025. Okay. So now we'll substitute S and NS in this equation N. So N is nothing but the speed of the rotor or speed of the motor. Okay, both are same. So 1 minus 0.025 multiplied by 600 RPM. Okay. So this will give you 585 RPM. Okay. Third one, a three-phase 4-pole 400 volts 50 Hz squirrel cage induction motor is operating at a slip of 0.02. The speed of the rotor. Okay. The speed of the rotor flux. Okay. Speed of the rotor flux in mechanical radians per second sensed by the stationary observer is closest to these options are A 1500, B 1470, C 157 and D 154. Okay. So we have to find out the speed of the rotor flux. Okay. Here in the case of an induction motor, the speed of the rotating magnetic field is a synchronous speed. Okay. So this magnetic field or magnetic flux will link with the rotor. Okay, so the speed will be same for both the stator flux as well as the rotor flux. So we have to find out the synchronous speed here in radians per second. Okay, the unit should be radians per second. So first we'll write the given data. So first the number of poles P. Number of pole P is equal to 4. And then the supply voltage is given. Okay, so the supply voltage is 400 volts. So next frequency. Supply frequency is 50 Hz and then the slip is equal to 0.02. So we have to find out the synchronous speed. Okay. So synchronous speed in radians per second is omega s. So that is equal to 2 pi ns divided by 60. Okay. First we'll find out ns value. So we all know the formula for ns. So ns is equal to 120 f by p. So 120 into 50 divided by 4. So this will be equal to 1500 rpm. Okay. So now omega s is equal to 2 pi into 1500 divided by 60. So this will be equal to 157 radians per second. So answer is C. Okay. So next, fourth one. A 4-pole induction machine is working as an induction generator. So the generator supply frequency is 60 Hz. The rotor current frequency is 5 Hz. So the mechanical speed of the rotor in RPM is dash. Okay, we have to find out the speed of the motor. Okay, so here the given data is, it is an induction generator. So whenever the induction machine acts as an induction generator, the slip will be in negative. Okay, so first we'll write down the given data. So the supply frequency, that is the frequency of the generator, is nothing but the supply frequency 60 Hertz. It is given. Number of poles P is equal to 4. And then the rotor current frequency, that is FR, is equal to 5 Hertz. So now we have to find out the speed of the rotor in RPM. Okay. So as usual, we have to write this N. Here, this is induction generator. So we will be writing it as 1 minus of S, okay, into Ns. So this is equal to 1 plus S into Ns. Okay. So in the case of induction generator, the slip will be negative. Okay. So first we will find Ns as usual, 120 F by P. So 120 into 60 divided by 4. Okay. So this will be equal to 1800 rpm. So next we have to find out the slip. So we know that Fr is equal to S times F. So from this expression, S is equal to Fr by F. So which is nothing but 5 by 60 or 1 by 12. So that will be equal to 0.0833. Okay. So now on substitution, we'll get N is equal to 1 plus 0.0833 multiplied by 1800 rpm. So this will give you 1949.9. So which is approximately 1950 rpm. So the answer is again C. So the next one, 220 volts, 8 pole, 50 Hertz, 3-phase star connected wound rotor induction motor has a rotor impedance of 0.02 plus J 0.08 ohms per phase at standstill. Okay, under standstill condition, we are getting this impedance, and as a negligible stator impedance. Okay, so now the maximum torque developed by the motor is dash. So we have to find out the maximum torque developed by the motor. Okay, so first we'll write the given data. So the supply voltage is given, V is equal to 220 volts. Number of poles P is equal to 8. The supply frequency F is equal to 50 Hertz. So the motor is star connected. Okay, in the case of star connection, VL is equal to √3 times V phase. So the motor has a rotor impedance per phase. Okay, it's per phase value. So under standstill condition, so the impedance under standstill condition can be written as R2 plus JX2. So we can write R2 as 0.02 ohms and X2 as 0.08 ohms. Okay. So now we have to find out the maximum torque developed by the motor. So the maximum torque developed by the motor can be written as K is a constant, into Sm E2 square R2. Sm is nothing but the slip corresponding to maximum torque divided by R2 square plus Sm into X2 whole square. Okay. So here K is nothing but the constant given by 3 divided by 2 pi into small ns. Small ns is nothing but the synchronous speed in RPS. Okay, revolutions per second. into Sm into E2 square R2 divided by R2 square plus Sm x2 whole square. Okay. So first we have to find out the synchronous speed. So first we'll find out the synchronous speed in RPM. Okay, Ns is equal to 120 F by P. So 120 into 50 divided by number of poles P is 8. So this will be equal to 750 RPM. Now we have to convert this into RPS. Okay, so this is equal to Ns by 60. So 750 divided by 60 will give you 12.5 RPS, revolutions per second. So next we'll find Sm. Okay, Sm is nothing but the slip corresponding to maximum torque. Okay, Sm is equal to R2 divided by X2. So 0.02 divided by 0.08. Okay, so on simplification we'll get the slip corresponding to maximum torque will be 0.25. Okay, so now we'll substitute in the torque equation. Okay, Tm is equal to 3 divided by 2 pi into 12.5 multiplied by 0.25 into E2. So E2 here it is given as a star connected machine. Okay, the motor is star connected. So in that case, this supply voltage is the line value unless otherwise specified. It should be taken as a line value. So VL is equal to 220 volts. So now we have to convert this into V phase. So this is 220 divided by root 3. Okay, V phase is equal to VL by root 3 in the case of star connection. So 220 by root 3 will give you 127.021 volts. Okay, so this E2 will be approximately equal to the supply voltage. Okay, so in place of E2 square we are going to substitute supply voltage only, 127.021 whole square into R2 value is 0.02. So whole divided by 0.02 whole square plus 0.25 into 0.08 whole square. Okay, so on simplification we'll be getting 242.01502 in the numerator divided by 0.0628 in the denominator. So dividing these two we'll get 3853.74 Newton meter. So this is the value of maximum torque.